All right, let's get right into it. Today, we're going deep inside the engine of modern AI. And forget all the big headlines for a second, because we're going to zoom in on one tiny, almost hidden mathematical detail in the famous attention formula. It looks like nothing, right? But I promise you, without it, the massive models we talk about every day, well, they just wouldn't work. They'd completely fall apart.
So here it is. This is the formula that's at the heart of pretty much all the major AI breakthroughs recently. And that little piece right there, that division by the square root of d sub k, that's our mystery. It seems so random, doesn't it? Just this little tweak. But that tiny operation is the secret ingredient, the stabilizer, that keeps these giant billion-parameter models from just completely breaking during training. So the question is, what on earth is it actually doing?
To figure this out, we first need to understand the villain of our story. And believe it or not, the villain is something super basic. A mathematical operation you probably learned a while ago, the dot product. But it has a surprisingly chaotic side.
You see, whenever an AI is trying to figure out a sentence, it has to know which words relate to which other words, like river and bank. The way it does this is by basically smashing together two giant grids of numbers, the query matrix and the key matrix. This involves doing millions of these little dot product calculations. And right there, at that massive scale, that's where the trouble starts.
Now, the problem isn't the dot product itself. The real problem, the trap, is what happens when you use it with the kind of high-dimensional vectors that AI needs to actually get smart. An AI can't just think in 2D or 3D, it needs hundreds of dimensions to grasp complex ideas. And in those strange, high-dimensional spaces, well, the math starts to get really weird.
Okay, so here's the one rule you have to get. The variance, which is just a fancy word for how spread out the results are, it grows in a straight line with the vector dimension dk. So if you double the dimensions, you pretty much double the spread of your scores. It's this runaway explosion of chaos.
And hey, this isn't just theory. Look at this. In 3D, your scores are in a nice, tight little package. Jump up to 100 dimensions, and that spread doubles. By the time you get to 1,000 dimensions, the scores are flying all over the place, from -30 to +30. The variance is just huge.
This chart just makes it super obvious, right? As the dimensions go up, the variance just keeps climbing and climbing. It's like a runaway train, and if we don't do something to stop it, it's about to slam right into the next step in the process.
And let's be super clear, we're not talking about some abstract problem at 1,000 dimensions. A totally normal, typical dimension for models you use every single day is 512. So this high variance issue isn't some hypothetical. It is a very real, very present danger to making these things work at all.
So, what happens next? This is where that exploding variance causes a catastrophic chain reaction. All those chaotic, spread-out scores get fed into the next piece of the puzzle, a function called Softmax. And Softmax, it does not like high variance at all.
The job of Softmax is pretty simple, really. It takes all those raw scores and turns them into nice, clean probabilities that all add up to 1. You can think of it like a stage manager with a spotlight. Its job is to find the most important word and shine a bright light on it. But how it behaves depends entirely on the input it gets.
And here's the crisis. If you give Softmax low variance input, scores that are all kind of close together, it gives you balanced probabilities, like 48%, 52%. But if you feed it those high variance scores that are super far apart, it just snaps. It goes into this extreme winner-take-all mode. It gives almost 100% probability to one single score and basically 0 to everything else. The spotlight becomes a laser, and it just burns away all the other context.
Imagine a classroom with a bunch of really tall students and a bunch of really short students. The teacher, that's our training process, can only see and pay attention to the tallest kids, the scores that got that nearly 100% probability. So what happens to everyone else? They're completely ignored. They never get a chance to contribute, and the whole class learns unevenly.
In machine learning, this disaster has a name, the vanishing gradient problem. Gradients are the learning signals that get sent back through the model. But for all those ignored scores, the signal becomes so tiny, so faint, that it basically vanishes into nothing. The model stops getting feedback, it stops learning, and the whole training process just grinds to a halt. It breaks.
So, that's the villain and the crisis it creates. It's a huge problem. But now, we get to the hero of the story. An incredibly simple, just mathematically beautiful solution that perfectly neutralizes this high-variance villain.
So what do we actually want to achieve here? Well, we want the best of both worlds, right? We want the deep understanding you get from using high dimensions, but we need to get rid of that chaotic, exploding variance. We have to tame it to keep it predictable and stable, whether we're using 3 dimensions or 512.
And the answer, it turns out, was hiding in a core principle of statistics. There's this rule that says when you multiply a variable by some number, let's call it c, its variance doesn't just multiply by c, it multiplies by c squared. And that little detail, that exponent, that's the key to everything.
Okay, let's just walk through this because it's just so clever. We know our variance is exploding by a factor of dk. So we need to multiply our scores by some number c so that c squared equals 1 over dk. Well, what number, when you square it, gives you 1 over dk? The answer is 1 over the square root of dk. So you square that, the dk from the problem, and the dk from the solution perfectly cancel each other out. And just like that, the variance is tamed. It's the perfect mathematical counterpunch.
So now that we see how it works, let's just step back for a second and appreciate what a massive impact this one simple division has had on, well, everything in AI.
I mean, this isn't some minor bug fix. This is so fundamental that they literally baked it right into the name of the whole mechanism. It's not just called dot product attention. It's called scaled dot product attention. That one word, scaled, isn't an afterthought. It's the whole game. It's the key innovation.
At the end of the day, this one tiny little detail unlocks everything we think of as modern AI. It's what allows models to use these massive high-dimensional vectors to really understand complex meaning. It's what keeps the training of models like GPT-4 stable. It completely prevents that vanishing gradient problem. This is the secret stabilizer that makes the whole AI revolution we're living through even possible.
And that kind of leaves us with a pretty cool thought, doesn't it? The whole story of scaled attention just goes to show how digging in and understanding one tiny fundamental principle can just unleash these massive breakthroughs. It really makes you wonder, what other small details are out there hiding in the math of AI, just waiting for someone to find them and unlock the next revolution?